So today's example involves a collision analysis of a collision from the laboratory, and this is the third setup where we had two carts of equal or approximately equal masses, M1 and M2, that are moving toward each other. M1 initially has a positive velocity, M2 initially has a negative velocity, and they come in and bounce off each other and head off in the opposite directions. Now, I want to do a theoretical versus experimental comparison between what actually happened in the collision and what I would expect. And this is a special type of collision called a partially elastic collision or an inelastic collision, but not perfectly inelastic. And a good parameter that describes or characterizes a partially elastic collision is the elasticity. So we're going to compare the relative velocity of these two carts before versus after the collision. And what happens in a collision is the relative velocity initial value gets multiplied by the elasticity and flipped around in the opposite direction to become the relative velocity in the final state. So we have to calculate these relative velocities, that is, the velocity of one cart relative to the other. So let's do it for the initial state, and that would be cart 1's velocity minus cart 2's velocity, the 0.77 minus a negative 0.67, turns into addition and comes up with a result of 1.44 meters per second. And then in the final state, we have the subtraction of the velocities is a negative velocity minus a positive velocity, which gives a very negative 1.08 meter per second velocity. And then if we plug those into the elasticity formula, we see that the minus sign is definitely still there, and we can just divide 1.08 over 1.44 after canceling the minus signs to get a collision elasticity of 0.75, or a 75% elastic collision. So let's predict what the 75% elastic collision should look like in the end if it's ideal. So we'll calculate the total momentum. So that's the 0.16 times 0.77 plus 0.16 times minus 0.67 is equal to 0.016 kilogram meters per second. So then what do we do with that total momentum? The total momentum is m total v center of mass. So that means v center of mass, which is like a collective velocity for both objects, but it's not the relative velocity, this 1.44, it's kind of an average velocity. That is p total over m total is equal to 0.016 over 0.32, which is 0.05 meters per second. So even though the one object is moving plus 0.77 meters per second, the other object is moving minus 0.67, their average is plus 0.05. Now we can calculate v1 initial prime. We can calculate v1's velocity relative to the center of mass. That's v1 initial minus v center of mass is 0.77 minus 0.05 is 0.72 meters per second. Now we can figure out what happens to v1 after the collision. v1 final prime is minus elasticity times v1 initial prime. In the perfectly elastic collision, all we have to do is put a minus sign on this number. But in the 75% elastic collision, we have to put in the minus sign and the 75%, and then the 0.72. So then that number is I need to have elasticity, and I need to multiply by elasticity equals minus elasticity times the initial is minus 0.54 meters per second. So in this step, we converted from a regular velocity, 0.77, to a primed relative velocity, or a velocity relative to the center of mass. We have to convert back now because this is a primed relative velocity. So V1 final is equal to V1 final prime plus V center of mass. If you subtract the center of mass velocity to find the prime version, then you add the center of mass velocity to get rid of the prime mark. So then this is minus 0.54 plus 0.05, which is minus 0.49 meters per second. And compare this to the measured value of minus 0.53 meters per second. And there's about a 10% difference here. It's not that bad. Maybe it's a little under a 10% difference because they're different from by 0.04 out of about 0.5. So it's about an 8% difference. But what's the total momentum? So the total momentum is measured P total final is the 0.16 times minus 0.53 plus 0.16 times, what was the other one? 0.55? 0.55. So 0.16 times minus 0.53 plus 0.16 times 0.55 is 0.0032 meters per second. So compare this to the initial total momentum of 0.016 kilogram meters per second, and we see that they're definitely different from each other. I feel like there might be something wrong here. So I'm just going to recalculate it and make sure. Yeah, that's correct. So that small error in the measured velocity, caused a huge percent error in the measured momentum. And this is something that happens when you're subtracting large values. So our P total final is equal to, if I just break out the momentum 1, it would be minus 0.0848 plus. And if I break out just momentum 2, 0.088. And that's the 0.0032. So effectively, here we're subtracting similar values. And we're getting a small result as a consequence of that. And this has the effect of amplifying the percent error. Because any error in subtraction is always added. And now that we've subtracted these things, we have about the same absolute error in our result. I mean, it's twice as big because we had two things with error, but it's when you calculate the percent error at the end, it's a larger portion of the result. So this is something that happens in lots of scientific calculations in all fields. It's not just a physics thing. And it's something you have to be very careful about. Imagine if I wanted to measure the, I don't know, the thickness of a wall. So if I wanted to measure the thickness of the wall of a building, so I might use a tape measure and measure the inside of the building, and then use a tape measure to measure the outside of the building and subtract, and that would give me the total wall thickness. But by measuring two very large quantities like that, it does this. It would amplify the amount of error involved. So anytime that you have two large measurements and subtract them, that smaller result that you get out of this subtraction suffers from that kind of a problem where it ends up having more error.